All right, let's do this. Secant of x minus 1, secant of x plus 1. So we have two factors, one term. X is the angle. We want to get that down somehow to a single power of a single trig function. So remember, we did one yesterday, two different ways. It's just kind of a combination of doing some algebra steps, right, with an expression. So factor, expand, combine like terms, divide out common factors, multiply by a clever form of 1, add a clever form of 0. That's pretty much it. Then the other thing is replacing something with what it's equivalent to, called an identity. And so the first way we did it yesterday was algebra. We factored out, and then we used Papa Pid, who was slapping us in the face. And then we did it the other way, where we actually did the substitution first, and then we did some algebra. So notice you factored on one side, you expanded on the other. They're both correct. They're both totally permissible. Neither one of them is necessarily shorter than the other, so you just have to find a way. So let's come over here and think about what we could do. We could do some trig replacements right out of the box, right? We know secant of x is the same as what? Reciprocal identity. What is it? 1 over cosine. Now, if you change that to 1 over cosine, you don't have to write this down, but look what would happen. You get 1 over cosine of x minus 1 and 1 over cosine of x plus 1. How's that looking to you? Is that looking better or worse? It's kind of looking worse because you're introducing fractions. So maybe, it's better than doing nothing, but is there any obvious quote-unquote algebra we could do here? You just did the expand it, right? You just did the arc. We don't always necessarily have to call it foiling, but we're distributing, right? We're multiplying. And you also want to kind of be perceptive of special products. That's secant x minus 1 and secant x plus 1. And those then are what conjugates of each other? Conjugates, right? Very good. Well, that's the first term, right? Remember when you multiply two conjugates together, like x minus 2, x plus 2, you end up with a difference of squares, always. The product of two conjugates gives you a difference of squares. So let's go ahead and expand it out. Secant times secant is secant squared, and we write it like that. Okay, that's how you write it. The squared goes between the secant and the x. The inner and outer terms you don't even have to mess with in this case because they are going to cancel, right? And you can verify in your head. You get minus secant on the inside plus secant on the outside. They cancel. They give you a 0. And so then it's just the last negative 1 times positive 1 is negative 1. So that's not looking bad at all. We want to get it down to a single power of a single trig function. So right now we have two terms. How can we get that into one term? Well, now that it's squared, anytime you have a squared trig function, especially in the presence of the number 1, do we have any identities that deal with squared trig functions that involve the number 1? They're the PIDs, right? The PIDs. They're going to show up quite a bit. So remember, you're not just memorizing that cosine squared plus sine squared is 1 and the other 2. What you need to understand is that you can relate cosine squared to sine squared and vice versa. You can always relate tangent squared to secant squared, and you can always relate cosecant squared to cotangent squared. So let's come down here, and where are we? Right here. Okay. So if you need to write it off to the side, secant squared. Okay, so baby PID number 1, remember, was 1 plus tangent squared of x, and it equals secant squared of x, right? So that's the one that you're recalling from memory, and that's the form that you learned it in. So you could do one of two things now. You can actually make a replacement, right? So let's do that. I'll go down this fork. If you replace secant squared with 1 plus tangent squared, you'll get 1 plus tangent squared, okay? And then you get minus 1. That's still there. And now what is 1 minus 1? 0. So we're just left with tangent squared. And that is a single power of a trig function. Now, you're going to be working with these Pythagorean identities so often that you're going to just realize that, hey, secant squared minus 1, bless you, Just like yesterday, remember, we replaced cosine squared with 1 minus sine squared. We kind of modified the original form. You can do the same thing here. Secant squared, if you just bring the 1 across, you get secant squared minus 1. What's secant squared minus 1 equal to? Tangent squared. So you could actually just go straight to tangent squared because you've solved the baby PID in your head, okay? But either way, whether you want to replace it and then subtract the 1s, or just do it in your head and call tangent squared. Either one is correct, right? So there you go. So look for special factors, conjugates. They're always going to give you difference of squares. And every one of the PIDs can be a difference of squares, okay? Now, it also might sometimes work in reverse. So also be aware that you can call tangent squared secant squared minus 1. And then be aware that secant squared minus 1 is a difference of 2 squares, which then could be factored into the product of 2 conjugates. So these things that we're doing are two-way paths. So we need to kind of, we're making these connections, right? And now that we've opened up these neural pathways, we could travel along them in either direction, okay? Any comments or questions on that? All right, letter C. I don't want to just take the fun out of it, but we are still in the nascent rudimentary stages, the inchoate stages, right, of learning this stuff. So why don't I just do this? I'll give you 1 minute to size it up, to think about what you could possibly do, and then we'll talk about it, okay? There you go. 1 minute. What would you do? You're trying to get that down to a single power of a trig function. So when you're simplifying these things, you don't want to put things back in terms of x, y, and r, like we did when we were proving the fundamental identities. You actually want to use the fundamental identities to manipulate this, okay? So if you look at it, you might say this is kind of disgusting. It's kind of gross, right? It's got fractions in it, right? Yucky, yucky, gross, gross. And it's got negative angles in it. Yucky, yucky, gross, gross. So your first step might be to make it more palatable, if you will, by possibly getting rid of fractions and or negative angles, right? We'll see. So we have 2 factors. So let's just see if we could do any construction work inside. 1 over cosine, 1 over cosine. That's the same as what? Secant. So I'm not sure if this is the right thing to do, but I'm going to replace it with secant. So at least now it doesn't have a fraction. Now I'm just going to leave that as 1. If I wanted to, I could call that cosine squared plus sine squared, right? Would that be beneficial here? Probably not. So I'm going to hold off on that, right? I could also call it e to the 0. Would that work? No, probably not. I'm just going to hold off, right? Now over here, I got cosine squared. I'm just going to, he looks okay. He's harmless. And then, oh my gosh, I have a negative angle. Whenever you have negative angles, you're going to probably want to get rid of them. Which identities do we use for dealing with negative angles? Odd even identities. Good. So is secant even or odd? It's even. Cosine and secant are even. Remember, secant spelled backwards is cosine, right? S-E-C is kiss backwards. So cosine and secant are the only 2 even. That means that the negative inside what? Comes out front or goes away? It just goes away. Cool. So we're just left with plus secant of theta. And now plus, ooh, yucky, yucky, gross, gross, I have another fraction. 1 over cosecant squared can be written as what? Sine squared. Good. Remember the ratio identities and the reciprocal identities can work for any powers. All right, so we went through, we just cleaned it up a little bit. And now, what? Anyone see anything? Yep, there you go. There's Papa Pitt again. He's showing up. Now, they don't have to be written side by side, right? Because the associative and commutative property of addition allows them to float. As long as they're terms, and they are, cosine squared plus sine squared is equal to 1. So let's just let this guy kind of rest, and let's go ahead and say that we still have the secant of theta that's in there, but now cosine squared plus sine squared becomes plus 1. And so now I'm down to that. And now it's a little bit of deja vu, isn't it? Oh, no, not 0. Ah, right. We've reduced it now to a problem that we've already done, which is part B. Okay? So again, if you just want to distribute, those are conjugates. We're just in terms of theta this time instead of x. Secant squared minus 1 is tangent squared. So they were pretty much the exact same thing. So here's what we've actually said then. We can now say that secant x minus 1 times secant x plus 1 is equal to that thing on the right. That's an identity. Whenever you see this, you can replace it with the thing on the right, or vice versa. Or you can replace either one of them with tangent squared. Pretty neat. Pretty neat. That was a pretty good disguise, right? I didn't recognize tangent squared when we started part C, but yet it was equivalent, right? Okay. He dressed up nicely, just like y'all are going to do all next week, right? Sweet. Okay. So we go over the day so you can start planning your outfits over the weekend? All right? Yeah, I think I told them to you, but might as well do it again. All right? So number 1 is Memes Day Monday, right? Vine, meme, whatever. Tuesday is Protect Yourself from Nature. So wear all of your, like wear your rain suit or something like that. Glasses, whatever. Yeah, Wednesday is wear your concert t-shirt. Thursday is wear your jersey and your cap. You can wear a ball cap. And then Friday, don't come to school. Okay, wear whatever you want. Sweet. And class colors for juniors are blue, right? Seniors are black. All right, move. What's that? Yep. The sophomores are white this year. They've been purple in the past, but they've changed. And the freshmen are still green, lime green. Yeah. Well, we made them green because they're green. They're like greenhorns, wet behind the ears. Huh? Y'all never heard either of those? Yeah, that means they're young and they're inexperienced. That's what green means. I'm still green. It's like you're talking about a branch, it's green, it's still growing, it's not mature, like a sapling. Wet behind the ears, that means inexperienced too. I guess more experienced people have dried their ears, especially behind it, right? Like, hand me a towel, I need to dry behind my ears. Oh, you're experienced now. I'm not sure where that comes from, wet behind the ears. Does that mean like they're just recently given birth and they still have like placenta on them? Oh, no, yeah, Lauren's shaking her head no again. We didn't have to go there. All right, I'm actually feeling better today, so let's see if we can stay on track. Okay, good. All right. By the way, I went to. It's funny. Just a little aside here. I had to leave early yesterday to go to physical therapist. My doctor said I should go try physical therapy for my concussion because I'm still having symptoms in my back and neck. A lot of whiplash, and so I went there, and it was like a reunion. I saw a student that graduated in 2008. She had torn her ACL for the 3rd time. She was there on her last day, and so got to talk to her. And then who else is there doing some training was Anna Kensing, who had just 30 minutes earlier left my class, calculus class, to go do that. So we were reunited. She was working there. And then as I was about to leave, who walks in like he owns the place? Jack Lewis, right? Yeah. So man, it was just like, wow, I was walking around talking to everybody. I thought we would just start a little calculus lesson in the corner. Um, but yeah, and anyway, it was kind of interesting, kind of fun. Well, they put me with a lady who is a concussion expert, but I got like whiplash from hitting my head so hard. So like I compressed my neck, and so I have like pinched nerves. Oh, it's a stupid story. I fell out of my truck. Yeah, and my foot got caught, so like a hinge, it was like, yeah, I pounded my head really, really hard. Oh, my ankle's fine actually. But yeah, so my neck is messed up. The muscles are overcompensating on one side. It's whiplash. So anyway, that's what I was there for. But yeah, a lot of people they make good money there. There's big business in accidents, right? Yep. Okay. Um, we got this one. 1 minus sine squared over cosecant squared minus 1. These ones divide out like that, right? No, not even, not even. Okay. So what to do? The good news is it's already one term. It's just something. But in the numerator, I have two terms. In the denominator, I have two terms. Oh my goodness. Can we do anything? Remember, if you ever have a squared trig function, especially in the presence of the number 1, you should be thinking, not Papa John, creepy, Papa Murphy, no, Papa Pig, right? Or Peppa Pig. So what is 1 minus sine squared equal to? Okay, so we'll do it one more time. You're going to get used to this. Cosine squared plus sine squared equals 1. So 1 minus sine squared is equal to what? Cosine squared. Yeah, you'll get really good at just seeing different versions of the PIDs, okay? All right, so that's cosine squared. And then cosecant squared. Wasn't there a PID with cosecant? Let's write it over here. From memory, it's 1 plus cotangent squared equals cosecant squared. Okay, that's the PID as we learned it. So what is cosecant squared minus 1? Cotangent squared. Good. See how we do that? If you need to write them off to the side, especially in the beginning, that's fine. But you know that there is an identity that you could use. So it's in your mental catalog, all right? You know it's accessible. So the good news is now we got it down to not just a single term, but single terms in the top and bottom. And now good things happen. The C's divide out, the O's divide out, the squareds divide out, the X's divide out, and we're left with S over T. Right? Yeah. 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 That's kind of funny, right? They have a lot of shared letters, but that's not right. So, what to do? What to do? Well, that's not quite the answer. Here's a new strategy. Okay, when in doubt, this is kind of like the ultimate save yourself strategy. You could use it in the beginning, but it also helps at some point to put everything, especially eggs, in one basket. No, put everything. It's Easter. Easter's coming up in terms of sine and cosine. You might have realized that every single trig function can be written in terms of sine and cosine. That's why on the unit circle, we only needed to know the cosine value, the x-coordinate, and the sine sine value, the y-coordinate, because we can get the other 4 trig functions by just knowing sine and cosine. So the numerator is already cosine, so we're not going to mess with it. Draw your big division bar. Now, what is cotangent squared in terms of sine and cosine? How would you find cotangent if I asked you to find it on the unit circle? X over y. Well, what is x? X is cosine, and y is sine. So you already know this. Remember, I told you already know that. You just have to, instead of thinking about it in terms of x over y, you got to think about it now in terms of cosine over sine, because the x is the cosine, the y is the sine. So cotangent is cosine over sine. So let's come down here, and we'll call it, because it's squared, it's going to be cosine squared of x all over sine squared of x. Okay, and notice the blue line is longer, that's the main division bar. And as I said yesterday, when you do this, that was a trig identity substitution, you create a complex fraction, you should be excited, you should be happy, because you know that the very next step is to eradicate the complex fraction algebraically. So you could do lick 'em over lick 'em, or in this case, you could do state change flip, right? Because it's just a single term in the bottom. So let's do that. So cosine squared in the top, you stay, and then the main division bar is going to turn to multiplication, and then we flip cosine squared over sine squared, and it becomes sine squared of x over cosine squared of x. Now notice the cosine's hanging out there by itself. You could put it over 1, right? It's the same thing as saying that that's over 1 up there. So stay, change, flip. Does that help? Yeah, what can we do now? Divide out, and we're left with sine squared of x. Wow. So this entire thing up here is sine squared of x. They're one and the same. It's an identity. So right now we're just kind of simplifying, but when we get to the next section, you're going to start with this. You're going to have the right side. You're going to have a definitive target. And so you'll just draw the line down like this, and now that's essentially the proof, right? So in one sense, proofs are going to be easier than what we're doing now. Because right now we just have vague targets, right? Single power of a trig function. When we do trig proofs, it's going to be like, I need to get sine squared. I have an actual goal, okay? So there you go. Putting everything in terms of sine and cosine is a good strategy. You could have done that from the very beginning. I don't know if I would have done that, called cosecant squared 1 over sine squared, because then you wouldn't have been able to do state change flip because it was 2 terms. But, you know, you had the option. All right. Letter E. If you get stuck right away, you might want to put it in terms of sine and cosine. Oh, wait, it already is. So let me give you a little tip here, a little guidance, and then I'll see if you could do it on your own. We're trying to get it down again to a single power of a single trig function, right? We want it to be like something trig to some power of x. So I need to get a single term. My final target has to be a single term. So here's another strategy. If you have 2 terms, and at least one of them is a fraction, you can get one term by combining them. And to do that, you need a what? Common denominator, okay? So go ahead and see if you can work on that. Maybe get a common denominator if you want, and go from there, okay? Give you a minute or two. And remember, you could, if you have co-prime denominators, which we do, 1 minus sine of x and cosine of x don't have anything in common with each other other than 1, you could do your crisscross butterfly method, applesauce butterfly cross. Yes, Amanda, 2 questions? No. Oh, okay. Just stretching, okay. Yeah, if you're taking the ACT tomorrow, you're welcome to borrow a calculator. A couple of you have already talked to me. And remember that magic link under the Monday mail takes you to ACT practice questions. So you can have a date with the shared folder tonight. I hope you like pizza, shared folder, because I'm treating you. I told y'all the other day that some of y'all were going to be inclined to make mistakes. And I said, avoid the temptation. Avoid the temptation. Over here we have 1 minus sine of x. Is that the same as cosine? Is that the same as cosine squared? No. Remember, the Pythagorean identities have to be squared. They have to be squared. If this were 1 minus sine squared, we could call it cosine squared. But remember, you just can't take the square root of each term. So if they're not squared, you can't use the Pythagorean identities. You can't call 1 minus sine cosine. And certainly you can't call cosine plus sine 1. They have to be squared. Okay? So let's go ahead and just get a common denominator. So you could do it this way. If you always start in the top left, you'll be safe. Take that product. Cosine times cosine is cosine squared. So there's your top left term. And then you take the other diagonal, sine times that. Now I'm not going to distribute yet because I'm not sure if I really want to. Okay, but it's going to be that. And then you take the middle sine. Okay, so if you always start in the top left, you're going to be good. Subtraction is not commutative. And in the bottom, you're going to have the product of those two, cosine of x times 1 minus sine of x. And that's how you can get it into a single term. That's one way to do it. Here's the other way to do it. Remember, and this is what y'all learned in little school. To get a common denominator, you just multiply by clever forms of 1, right? This one has the cosine. It needs a 1 minus sine. So you multiply by 1 minus sine over 1 minus sine. And then this one has the 1 minus sine. So you multiply by cosine over cosine. That's the correct way to do it. And if you want to do it that way, because that makes more sense, that's fine. Now you're going to have the same thing on the line right below. And now we reassess. So we got it down to one term. Now, again, there's going to be temptation, right? To go, oh, yeah. But does that, maybe just, there you go. Does that work, though? Do those divide out? Nope. Because 1 minus sine of x is a factor in the bottom, but it's part of a term in the top, and it's not common, so you can't do that. So here's what I would suggest. Go ahead and distribute the top and see what happens. And let's hold off on the bottom, okay? We may or may not want to distribute. What's nice about the bottom is it's completely factored. You see that? And we know that we could divide out common factors. So we might want to leave the bottom factored. The top is partially factored. So you do want to expand it out. So we got cosine squared. And if I distribute, I get minus sine of x. And then what is negative sine of x times negative sine of x? Positive sine squared of x. Now again, in the bottom, if you're not sure whether you need to distribute or not, don't distribute just yet until you get some insight from the top. If you have one side that's already completely factored, hold off on distributing it. But the numerator was partially factored. So maybe that's another strategy. We could say expand partially factored terms. Okay, and then leave others that are completely factored alone temporarily. And now we reassess. Anything good happening in the numerator? Whoopsh, whoopsh, look at me. Whoopsh, whoopsh. Mr. Pidd, right? You can call him Mr. Pidd. The Honorable Mr. Pidd, Papa Pidd. That's cosine squared plus sine squared. What does that equal to? 1. So I'm going to replace both of those with the number 1, and I'm still left with minus sine of x. And in the bottom, it's still completely factored. I'm going to leave it completely factored. Anything now? Actually, yeah. They do. So here's what you could do, and I'd prefer if you did this. Put those in parentheses and maybe just put 1 times that. Is that legal? Yes. So now the entire 1 minus sine of x factor, the whole thing, okay, they divide out. Okay, so let me add that strategy. Expand partially factored terms, and then another one, leave numerators, nums, and denominators, denoms, that are completely factored, leave them alone until there's a need to expand them. Because notice we were able to divide out the 1 minus sine of x's. And what are we left with? We're left with 1 over cosine. What's another name for 1 over cosine? Secant of x. And boom, there you have it. That is what we were looking for. So that original expression is exactly the same as secant. They're one and the same. Okay, so a couple of strategies there, right? Get a common denominator, expand partially factored terms, and then leave the denominators and numerators that are completely factored. Leave them alone temporarily. There might be a time later on where you want to expand them. All right, so you see kind of the fun factor is slowly building up, leading towards spring fling. That's right. Okay. Take it all in, let it soak. Let it soak. All right, everyone good? Ready for another? More, please. All right. All right, letter F. What the heck is that letter? Beta. Good. It reminds me of Tigger. It's like a bee on a pogo stick. This is beta. It's just another variable that we use, okay? We use x, we use theta, beta, alpha. Don't let the variable mess you up. In fact, if you don't like it, you can call it x. Just go through and change everything that's a beta to an x. Whatever you want to do. Or work it in terms of beta and expand your horizons. So I'm going to go ahead and let you chew on that for a minute or so. See if you can do anything with it based on some fundamental identities. Oh, yeah, that's right. We have notability, so we don't have to just cross out the betas. We can white them out first. Yeah, that's cool. Huh? Is it still there? Oh, maybe I need to go over it again? I do see it on the screen. I don't see it on my iPad. Oh, it's just the burned retina? Yeah. That's why you have screensavers. Yeah, okay. So I'm going to change it to lambda. Right? That's more palatable, right? Right. No, I'm going to put it back to beta. You can change it to whatever you want. Okay, let's see how y'all did. Let's see how you did. First thing I'm going to notice is that I've got some funky angles. I've got a negative beta that I'm going to work on. And then I have this pi halves minus beta. Pi halves minus something. What identities do we use for pi halves minus? The cofunction. Yeah, this is screaming cofunction right here. So let's go ahead and do that. We have a negative, and then what is the cofunction of tangent? Cotangent. So this piece here simply becomes cotangent of beta. Okay? So again, you have them memorized. That way when you see them, it kind of alerts you to a possibility. All right. I guess I should highlight the replacement. That becomes that. Now it's times. Now we have a negative angle, so that's going to be even-odd identity time. Is cosecant even or odd? It's odd. So the negative does what? Away or out front? Out front. Now you got to be careful. If you bring it just out front of that factor, it's going to look like this, cosecant of beta. And whenever you have dot negative, I will growl. From wherever I am, I will growl. Like Papa Bear when he came home and found out that Goldilocks had destroyed the house. Because that is going to look like subtraction instead of multiplication. So you have two choices. You can either put it in parentheses, or because y'all are astute students, you could bring the negative out front of the entire thing and just make that positive, right? That would be fine because it's all just one big term. So I'll do that on the next line. A negative times a negative makes it a positive. So I have cotangent of beta times cosecant of beta. That's what I have right now. Well, I'm supposed to get it down to a single trig function, and I have two trig functions. Oh, yeah, man, yeah. I am losing sight of it. Woo, I'm just so excited. So, yeah, you could do that. Just don't forget that there is another part. So I was so focused on working on the numerator, I forgot the denominator. Let's do the denominator now. Yeah. Cotangent squared plus 1. I have a squared trig function, and there's a presence of 1. Yeah, that one is straight up cosecant squared of beta. Cotangent squared plus 1 is straight up cosecant squared. We memorized it as 1 plus cotangent, but it's commutative. All right, so I do have cosecant squared in the bottom. Now that's two factors of cosecant. So I'm going to do this. I'm going to write cosecant squared as cosecant times cosecant. Why would I want to write cosecant squared as cosecant times cosecant? So you could divide one out. Okay? Looky there, looky there. So one of them divides out. Now, if you wanted to leave it as cosecant squared, that's fine. Divide out the one on the top, and then just draw a little line through the 2 and put a 1. Okay? But it's nicer when you can kind of take the whole thing away. All right, so we're left with cotangent over cosecant. I need to get that in terms of a single trig function. I don't know what to do. I'm kind of stuck at this point. What do they all have genetic DNA made up of? Sine and cosine. So when you want to collapse something down, put everything in terms of sine and cosine. Cotangent is cosine over sine, and then all over, that's not a good color, cosecant is 1 over sine. Okay, put everything in terms of sine and cosine. And now we've created a complex fraction, which means we say, hooray, hooray, it's my lucky day. Next week is spring fling. What else can I say? Yeah. State change flip, right? So cosine of beta over sine of beta times the reciprocal of 1 over sine is sine of beta over 1. Oh boy, what happens now? They divide out, and we are left with cosine of beta. Holy moly smokers. This whole thing was equal to cosine of beta. So, again, it's going to be easier when we start doing proofs. I'll just plant that idea in your head, because that's what it'll look like. You'll have that big ugly expression equaling cosine, and you'll have a definitive target. You'll know exactly what you're going to be working towards. Okay? And we're done with example 6. How do y'all feel? Y'all like that? It's kind of fun. It's better than Sudoku. Okay? Yeah, I played it once or twice. I didn't like it, so I do this more often than that. I do like crossword puzzles, but everyone thinks, hey, he's a math teacher. He must like Sudoku. Hate it.
I just really wanted to get through math class because as soon as we finished, it died.
Oh, really? Well, good. I'm glad it hung in there for what matters. Hey, speaking of what matters, next week is spring fling. I don't know if y'all know that. I want to see y'all dressed up in your memes on Monday, and we'll have a good time. Right? Teamwork makes the dream work, baby. So have a good, fun, safe weekend, whatever you're going to be working on, or if you're at Folk Fest making bricks or candles, um, or taking the ACT, good luck to you. Um, you're taking it what? Oh, a nap. Yeah, good luck with the nap. Don't oversleep.